Okay, I think it's about 6 o'clock. It's just about showtime here. I think I'm going to go ahead and get started. Thank you for those of you who have been able to um, make it over to my oh Tian, what are you saying? I mentioned the Zoom ID and the syllabus, so maybe many people can. I hope that everybody's attending. There's 30 people in here now. That's pretty darn good. So I'm hoping that people have been able to find their way over here. Um, yeah, I'm going to go ahead and get started. First of all, guys, thank you again for your patience with me during these first 2 weeks. My parents are recovering from some surgeries late last year, and they could really use my help around the house just to get on their feet again while we're starting up the new semester. So I have been doing my best to help them, but also well, to not quit my day job. So anyway, I'm glad to be here. I hope that you guys are all doing well. I did want to remind you that starting next week, we will be meeting back in person again. But for today and also for Thursday, we are still meeting in this same Zoom room, just like always. So you guys have obviously found your way over here, which is great. Tonight, you're going to have some opportunities to type into your chat box because I'm going to ask you guys some questions. And that is how I'm taking attendance tonight, by the way. And I am taking attendance because I am planning to drop students who are not showing up because I've got a waiting list and I want to get as many people in here as I can. So make sure that you uh, get some responses into chat tonight when I ask you for them. That would be super. Um, Let's see. Also, just a few announcements as we get started. My grader has had a chance to look at your first homework. You should have already gotten some feedback on homework number 1 that you turned in last Friday. Let me just explain how the grading is done so you know in case there's a question about it. Each assignment is worth 20 points, and you'll be getting some of those points just for submitting the homework complete, regardless of whether the math is whatever. It could be anything. So I think on this first assignment, my grader was giving out 6 points. By the way, I'm not the grader, right? My grader was giving out 6 points just for turning it in. So on the top of your paper, you might have seen a 6 somewhere. And then what he did for the other 14 points is my grader actually checked, I think he chose 3 problems and gave a credit based on how you were doing on those problems. So I think the first one was worth 6, and then the second one was worth 4, and then the third one was worth 4. So some of you might see something kind of like this on the top of your homework assignment that you got back on the grading. The handwriting could have been a little bit better. I'll talk to my grader about that. But anyway, there should have been like 4 numbers on the top of your paper. And if you got everything correct, you would have had them adding up to 20. And then that would be the points that you got on the assignment. I just want to let you know, even though I'm not the one grading your assignment, I, of course, can overrule my grader if you don't think your paper was graded correctly, or if a score was misrecorded, or anything like that as you're checking your grades in Canvas. Feel free to bring any of that type of stuff to my attention, and I will take a look at it and address whatever needs to be fixed. So anyway, I saw a lot of really good scores on the first assignment. That was awesome to see. But this sort of thing is what he might have written on the top of your paper. I just wanted you to kind of be aware of how that's going to be done. Speaking of homework, your second assignment is actually due tonight at midnight. I do have office hours after class. So right after 8 o'clock, I'm going to jump over to my office Zoom address, which is a different room than this one is. But I'll be jumping over there and hanging out to see if people have questions about the homework that you're working on for tonight. Of course, I'm happy to help out with any of that. If you have any questions that you already can think of now, feel free to drop them in the chat while we're kind of chatting here at the beginning of class. And I'm going to save a few minutes to look at a little bit of that with you. That certainly is fine. I did want to mention that on the homework, occasionally I've been asking some true false items, some items that are either true or false. I would want you in your solutions to do more than just say it's true or it's false. Please be sure to write a line or two to just give me a quick, okay, here's why it's true or here's why it's not true. I don't need a big long essay. You don't need to solve a whole big math problem, but just what's kind of your intuition behind it? Why is it? What's wrong with the statement? If it's false or if it's true, can you give me some reason to verify it? Maybe it's a result from the book or from lecture, or maybe you can just write it out in your own words in a line or two. I'm not going to be grading those really strictly, but there should be some justifications there. Okay. Whether the questions are true or false, you can find those answers in the back of the book. You can also find answers to any odd numbered problem in the back of the book. But what's really important, of course, is all of the work. You want to show your work. You want to be able to come back in the weeks ahead and reconstruct or reimagine what your thought process was into how you solve these problems. So be sure to show your work, of course, at all times. That's going to be a win-win for everybody. Okay, fantastic. Let me just see. There's still a couple people on the waiting list. At this point, the waiting list, the only way to get into this class is for me to sign an ad form. And of course, I'm eager and happy to do that. I just have to be careful about the classroom size because I know how big the room is that we're going to be going into. So I'm waiting. I am going to be dropping any people who are, there's already at least one person who hasn't shown up yet and didn't turn in any homework. So I need to clear up a spot there. If you're still trying to get into the class, we have until next Tuesday to get you added officially to the class. Remember that just being in Canvas doesn't mean you're on my roster yet. So there's a couple people in here who I think that might apply to. Anyway, I am happy to do the best I can to help out with all of that. Yeah, I think those are my main announcements. Does anybody have any questions so far about any of this sort of preamble stuff?
Dr. Anna, do you mind if I say something really fast? I'm sorry to interrupt your
No,
flow.
by all means, Audrey, go right ahead. This is my SI
Okay.
leader.
Yes. Hello again, everyone. Just wanted to say that there are some open seats in SI. So if you want to enroll officially, you're welcome to do that. If you also just want to stop by, I believe we're at a point where there are just enough spaces open for you to just come by for even one session, and just see what you think of it. I would highly recommend. I know a lot of people who are in it have been telling me feedback that they've learned a lot and it's been really helpful. So just wanted to let you know that there are some spots open.
Sweet. That's great to know. Okay, yeah, and that meets on Tuesdays and Thursdays at 4 o'clock. So
Yes.
shortly before class. It's a great way to kind of get yourself into the Math 250B mode before you come into lecture as well. So I think it's a good timing.
Yep.
And yeah, highly recommend that. Thank you, Audrey.
Yep.
Okay, and other than that, I don't have any other announcements for the moment. I did want to make sure, I hope that everybody got my email this morning. I'm gonna go ahead and pull something up here and share my screen in a minute. I hope that you all got my email this morning that has a handout on it. I decided to share this handout with you all. Hopefully you can see all of that. This was just a way to save me from having to write it all down on my whiteboard here behind me. And I think that this might be kind of a handy thing to use. It's a recap of chapter 1, basically, which is the stuff we learned about last week. And you can see that there are 4 different types of differential equations, right? And those are listed out in the left column on the left part of the page there. And what I've done is kind of given you a nice little summary of everything in one place. So the form of each of those 4 types of differential equations is in the second column. You guys watched videos about the separable and linear ones. And then for the Bernoulli and homogeneous ones, we talked about that on Thursday. And then the third column, which is really where the meat of all of this is the method to solve each of these types of differential equations. So for separable equations, we just have to integrate both sides of the separated form. For linear differential equations, the key tool is the integrating factor. that we learned about. And then on Thursday, I talked about this change of variables technique, and we have two slightly different change of variables approaches for the Bernoulli and homogeneous differential equations. So all of the sort of important equations are kind of on this handout. And then on the far right column, I just reminded you again about those applications that we've looked at already, the Newton's law of cooling, as well as the mixing problems as examples of separable and linear differential equations. So this is just kind of a all in one place handout. I've also put it into Canvas under the special handouts folder in case you lose track of it at some point. You can always dig this back out again. But I think you might find this quite helpful. You might want to keep it. I'm going to stop sharing my screen for now, but you might want to keep it somewhere close by for what we're going to do here right at the start of class tonight. I am going to have us work on group work number 3. You might wonder for a minute what happened to group work number 1 and group work number 2. Well, it turns out that I actually embedded those into the videos that you guys watched last week already. So we don't have to do the first 2 group works because I kind of already cheated and put them into the videos that you watched. Normally with group work, what I would be doing is getting you guys out of your chairs and having you work at the whiteboards around my room. And we'll start that next week. I will be getting up from time to time to have you guys practice the material on your own. In this case, however, since we're doing this through Zoom, I'm kind of going to just talk us through this a little bit. And so I might take just another minute and share my screen one more time, if that's reasonable. Let me go back again and where is my share button here? Yeah, let me just share my screen again. Hopefully this time you are seeing so a little bit more of the Canvas page. It's kind of like the home page here. And I'm in the files section actually. One of the folders in here is called GroupWorks. And so these are the GroupWorks that I've been referring to. Remember, these are not graded. These are just for us to practice with each other and to kind of take a break from new material to review old things. So I could open up group work number 3 right here, which is the one that we're going to talk about right now. And, there's just a little bit of work for us to practice here. What this is saying on this group work is they want you to take the differential equations that are listed there and they want you to decide, are they separable, linear, Bernoulli, or homogeneous? Okay, those are the 4 types that we just reviewed. And so I have actually taken the liberty, as you know, of putting those questions on my board right back here. So I think you don't need to have the group work open right now. But here's what I would like you guys to do. I am going to stop talking for about 2 minutes and let you guys take a look at these 3 differential equations that are from group work number 3. And I would like you to just try to identify which kind of equation they are, okay? You don't have to tell me right away if you know what it is, but just, I'm gonna be quiet for 2 minutes and let you guys try to classify them because that's a very important part of the process. So with that in mind, let's take 2 minutes. Use some scratch paper if you need to scribble around. There might be some algebra that you have to do. But see if you can get these into one of the forms of those 4 types of differential equations. In 2 minutes, we'll talk about it. All right, guys, that was about 2 minutes. I know you might not be done yet, and that's totally okay. But here's what I'd like to do. And do you all have a chat box access there on your Zoom screen somehow? This is how I'm going to take attendance tonight. I would like you all to put a word into your chat right now. We're going to look at number one. And don't worry about whether the answer is right or wrong. We're still learning, right? So don't feel nervous that you don't want to put an answer in there. I need you to put an answer in there, if nothing else, so I can record your attendance here tonight. What I want you to write is I want you to write either separable, linear, Bernoulli, or homogeneous, whichever one you think it is. And please send your message to everyone. And let's see what everybody has to say about it. And we'll see if there's any kind of consensus here, and then we'll chat about it. But I need everybody to put something in the chat so that I can just make sure that I know that you were here tonight. Okay, so we're getting a pretty good list. I'm going to wait another minute or so. Seems to be mostly a pretty good consensus. Well, there's two answers that have been very popular here, which are homogeneous and separable. Let me rewrite the equation a little bit bigger over here. Do you notice how the 3x minus 2y is in parentheses right here? You know, the fact that the 3x minus 2y is in parentheses actually means that you can't really pull them apart. Like you can't take the 3x and move it somewhere without also putting the 2y with it, right? Because it's all together as a quantity. And so you can't really separate the 3x from the 2y. So there were a few people who maybe thought this one was separable, but algebraically speaking, this one is pretty hard to separate because of that 3x minus 2y that's in those parentheses. So in fact, what we can do is we can rearrange this equation to solve it for dy over dx. And the reason to do that is that I see the rest of you put homogeneous down as your answer. If you want to test if it's homogeneous, you probably remember that what we have to do is we have to identify, f of x and y on the right-hand side all by itself. And then the test for homogeneous, I'm just reminding you from last Thursday, the way that works is I have to attach a t next to, I'm going to go ahead and do it here, next to every single x and every single y. So in the numerator, I would have 3yt, and in the denominator, I would have 3xt minus 2yt. And you might be starting to see how this algebra is going to play out for us, right? Because do you see that the t's can be factored? Right, so you can actually, on the bottom, you can factor that t out and then cancel it with the numerator. And what you've effectively done is you've removed the t from the expression completely, and you are right back to your original f of x and y again. So if you look at your little cheat sheet, that handout that I emailed you and that we looked at a few minutes ago, that's the test for homogeneous, right? So this one passes the test for homogeneous. I'm going to go ahead and put that down as our answer here. This one is homogeneous of degree 0. Absolutely, and most of you did have that down, which is awesome. So in this case, what we would do, I'm actually not going to solve this one right now, but if we wanted to solve it, we would implement the change of variables that we learned last Thursday. So y would be equal to x times v, and then y prime, which is just the derivative of that, is xv prime plus v. We would take that change of variables and sub it in, maybe to this one. Just take this one and plug in everything in terms of v. And remember that that change of variables will convert it into a separable differential equation. So yeah, that's exactly the idea behind that problem. Clear enough? Any questions on that one? Okay, let's move on to number 2 then. Maybe I'll give you an extra 30 seconds to think about number 2. We've already taken a little bit of time, but if you need to take a little more time, on number 2, you're going to have to do some algebra here to get it separated. Oh, you guys are way ahead of me. The chat is already blowing up with answers. Okay. That's all good. Oh my goodness. Well, it looks like you didn't need 30 more seconds. You've got a good idea about this one already. So it looks almost unanimous. I love it. And that is the right answer. This one is definitely Bernoulli on number 2. And it may not be obvious right away that it's Bernoulli, but what you have to do is, let me give myself a little more room again. You have to do a little algebra first to make it look like the form of a Bernoulli equation. So in this case, what you would probably do first is just distribute that y that you see right there. So this would become y prime plus tangent of x times y, and then plus sine of x times y squared equals 0. And if you remember the Bernoulli form, guys, you have to take the y, the power of y, and move it to the other side of the equal sign. So we would do one more step here, which is we would rewrite this as y prime plus the tangent of x times y. And then that would be equal to negative sine of x times y squared. And now it looks exactly like the form of a Bernoulli equation, right? The n value, in this case, that's just the power on that y right there, and that would be 2. So in this Bernoulli differential equation, we have a change of variables which is different. Namely, u equals y to the 1 minus n power. That's also on that handout that you have now. And the n here is 2. It's just the power of y. Okay, and so you can then implement that change of variables. You end up getting a linear differential equation, if you remember, which you can then solve using integrating factors. So yeah, that is a really good one. That one is Bernoulli. Okay, you guys are really quick. Let's look at number 3. Go ahead and use the chat box for this one as well. I love it. It is totally linear. It is absolutely totally linear. I'm seeing lots of answers. Hopefully everybody's typed into the chat at least once, so I have your attendance here tonight. But for sure, this is linear. I will point out that the form of a linear equation, let me just scribble over here again. The form of a linear equation is like such: y prime plus p of x times y equals q of x. This equation is not in that form quite yet because there's an x in front of the y prime. So one thing to keep in mind on this, guys, is that the first thing you'll want to do if you were going to solve this one is you would want to divide through by x. So you would end up getting something that looks like this, right? Y prime minus 2 over x times y equals 2x ln of x, okay? And now it's in the form that I put on the other board over here, and you can use the p of x and q of x and go through the process. Okay, everybody comfortable with that? Now, I'm going to go back and share my screen again because I just want to show you one other thing here that you may want to do. For anybody who wants to, you can practice these problems. So this is the group work that we just looked at right now. But it does say here, go back and solve as many of them as you can, right? So I'm just going to invite you to do that on your own if you want to or need to. There is a folder in Canvas that's called GroupWorks Solutions. So again, these are not graded, and I'm not trying to keep a secret of any of this stuff. I want you guys to have as many examples to review as possible, but I did type up full-blown worked out solutions. The first one's actually kind of nasty, to be honest with you. It's a fair messy bit of calculation there. So, be patient with yourself on that one if you try to do that one. No, number 2 is not too bad. It's just a short little bit of work here to solve that Bernoulli equation. And then the third one, even shorter, to solve this linear equation. So I just wanted to remind you, since we're still early in the semester, that Canvas has all this stuff in it, and you're certainly encouraged to poke your head around in there and find solutions to practice problems all over the place. So if anybody is bored this weekend and wants to practice some homogeneous or Bernoulli or linear equations, well, here you go. You've got a few more that you could take a look at there. Okay. Any other questions about this group work for now? Let's see, Daniel's got a question. If we need to identify the equations that are not in an obvious form, are there forms we should try to identify first when it's coming to crunch time or whatever? Honestly, it's kind of up to your preference. I usually just go in order. I sort of say, is this separable? Because that's the first thing I learned. And then after that, I ask myself, is it linear? Um, the linear and Bernoulli ones look very similar usually. And then the homogeneous and the separable ones can often look kind of similar too. So it's usually possible to kind of at least break it down into two groups of two. But I don't have a perfect answer to your question, Daniel. It's a really good one. I think just with your own time and experience, you'll get a little bit more comfortable with that. Fabiola, do you have a question for me?
Yeah, so from looking at the Bernoulli, like for me it was hard for I thought it was at linear first, but how do you know it's Bernoulli at first glance?
Oh, well, I didn't know it at first glance. That's the interesting thing. I had to do a little bit of algebra here first. Because if you look at the original question, there's a y here and a y right here. As soon as you're multiplying two y's together, it can't be linear anymore
Okay.
because that's not allowed for a linear one. But you're bringing up a good point, which is that I might not see that immediately. And so that's where sometimes a little bit of this algebra simplification can help you to make these decisions. You don't have to figure it out in a split second, right? I mean, I gave you guys 2 minutes to do all three of these, which honestly probably wasn't really that much time. So feel free to, take a breath and, analyze these equations from an algebra point of view a little bit more first.
Okay, thank you.
Yeah, great question. Okay, are we good on group work number 3? By the time we get to number 4, we will be back in person. So that'll be probably next week. We'll tackle group work number 4, which is about chapter 2. Let me give myself a little bit of room here. I so far haven't seen any problem numbers put into the chat, like homework questions people wanted me to go over. So I think I'm gonna assume there aren't any for the moment, and maybe during our break, remember, we'll take a 10-minute break here in a little while. Maybe if there is something that I missed, we can talk about it then. What I think I would like to do is actually move on to something new. As I mentioned on Thursday last week, we could spend the entire semester just doing what we've been doing, which is, well, I bring in a new differential equation and I show you what it looks like and I tell you how to solve it, and yay, we're happy with that. Then we go on to another one, and we could just do this forever, right? But I would much prefer to try to equip you guys with some way better tools, way more powerful, way more broadly applicable tools that will help you not just with differential equations, but with a lot of other stuff: computer graphics, data science, statistics, any kind of applied math. I mean, there's so many things that linear algebra is good for. So we are going to sort of take a detour now and spend basically until roughly mid-April, after spring break anyway. It'll be after spring break until we finally come back to differential equations as our primary focus. And I'm going to start chapter 2. So we're done with everything I'm going to cover in chapter 1. And I'm going to start talking now, guys, about chapter 2. And let me know if you're having trouble seeing any of these notes, by the way. If anything's not coming through, let me know. I might actually try to pin myself here on my side so I can make sure I'm seeing what I've got up here better. Chapter 2 is really just an introduction to linear algebra, just some very basic stuff. So this is called matrices and linear systems of equations. It's kind of a long title, right? Matrices and linear systems of equations. This is what we're going to be talking about this evening. So I'm gonna have a lot of definitions here, guys. I have to apologize ahead of time for that. There's quite a few of those. And this is gonna be fairly basic material. Some of you might have already learned about matrices. Maybe you know some basic, I mean, you've all solved systems of equations before. Trust me, in high school, you would have done that. So this is in some sense not going to be completely new to anybody. But I want to get the vocabulary out there. I want to kind of give you the spirit of kind of how we're going to be approaching this material and kind of what our goals are. So there will be some definitions, and I'm going to start right here with the first one. Okay, so the first definition that we need, and again, this is totally fish out of water. I'm now talking about something totally different than we did last week, right? What is a linear equation? I'm just going to start with this definition. A linear equation. Okay, so I always like to underline whatever the phrase is that I'm providing a definition for. A linear equation has the form, and now I'm going to write it down for you. A1 times x1 plus a2 times x2 plus dot 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 plus an times xn equals to b. Put that in a box. That's my linear equation. And when I write that down, I'm interpreting this as the xi's. Those xi's, those are the unknowns in my system. So those are my, or not my system, and those are the unknowns in my equation. And then the a sub i's and the b, those are to be thought of as given constants. So those are constants that are just given to us in the first place as part of the equation. Okay, so that is a linear equation. In a minute, I'll write down an actual example of that. But before I do an example, I have one more definition that goes right along with this one. So I want to just get it out of the way here. Namely, what do I mean by a linear system? It's part of the title of this chapter. A linear system, so this just goes right along with the first definition. A linear system of equations. Hopefully my handwriting is good enough. Are you guys able to read this okay? Reasonable? Okay, good. At least a couple people. Yeah, a linear system of equations. This is just a collection. It is a collection of linear equations. It's just a collection of linear equations, guys. That's all it is. It's just a bunch of them put together. Let's write down an example so we can kind of get a little bit of practice here. What if I had negative 3x plus 2y plus z minus w equals 5. That would be maybe, that's one equation, one linear equation. But maybe I have another one, 2x minus 2z equals 3. And then maybe one more, maybe I have negative y plus 5z plus 2w equals 0. So this is a linear system that has 3 equations in it. And I just wanted to have an example down. And I'm going to be working with this example as we go on. So you may want to get this jotted down. By the way, somebody in my first class asked me, do I have my notes for this material that I could just pass out? It turns out I do have notes written for me to understand, meaning that they are good enough that I can figure out what I'm supposed to be talking about, but I don't think they're good enough to just post up my lecture notes into Canvas. I'm not planning to do that. What you could do, it's up to you, but I've seen students in the past who have decided they don't want to take notes. They just want to take pictures of my whiteboards. You can certainly be doing that, right? Before I erase stuff, if you just want to grab a picture, feel free to use your phone anytime, just grab a snapshot. I see students who show up to class a little late sometimes, they'll do that. They'll come in and say, oh, before he erases it, I got to catch up and get a picture of it. That's totally okay. So anyway, yeah, I don't think my notes are suitable for dissemination in Canvas, but certainly I'm trying to write them on the board in a way that is easy for you to pick up. Yeah, so in this case, I only have 4 unknowns, which are X, Y, Z, and W. So I didn't call them X1, X2, X3, and X4 like I did in the general setup at the top. But this would be an example of a linear system. And I'm just gonna come right out with it, guys. What is the goal of this entire chapter? The goal of this entire chapter, my friends, is going to be to solve linear systems. Okay, so let's just write that down. The goal is to solve linear systems for the unknowns if we would like to solve what is X, what is Y, what is Z, and what is W. But I need to add a little caution note here, which is that there are some linear systems that we cannot solve. So I'm just going to put a little extra bit on the end of this, and I'm just going to say if possible. If possible. You don't have to use your imagination very much to come up with a linear system that it is impossible to solve, right? So let me just very quickly give you one more example here, and I think you'll see what I mean. What if my linear system was X plus Y equals 1 and X plus Y equals 2? I give you these equations and I ask you to solve for X and Y, right? I mean, that would be the way this would go. And as you can see, it is impossible. All right, this one is impossible to solve. So I'll just write here impossible. It's impossible to solve that, and so that's why I added that to the goal here. The goal is to solve these linear systems if possible, because sometimes it might not always be possible. Okay, so let me take a breath here and get this wiped off so we can write a little bit more on this side. Okay. And I am still keeping my eyes on the chat, so if you guys have any questions as I'm talking along here, just let me know. You can either use your microphone or you can, you can put them in the chat as well. So there is a definition then that I think is appropriate to get into the notes right at this point. So I'm gonna put this right here. When there is a solution to your system, we're gonna call that linear system consistent. Consistent. So let me add that here to the definition. A linear system is consistent. Consistent. It is consistent, right? If it has at least one solution. If there's at least one solution, we're going to call that system consistent. Otherwise, it is inconsistent. Okay, so anytime you have a linear system of equations, it's either going to be consistent or it's going to be inconsistent. The one that's in this example down here on the other side of my board, right? This one here, my friends, this one is inconsistent. Just going to add that word here into the whiteboard. This is an inconsistent system here on the bottom of that board there on the right side. So, yeah, so this is going to be a question we're going to be always asking in this class. Is our linear system consistent or inconsistent? In fact, there's going to be times, guys, especially later on in the course, where we actually don't even need to actually solve the system. We just want to know, does it have a solution or not? If there is a solution, we don't care what it is. We just want to know, is there one? Isn't that weird? If there was a solution, don't you think you would want to find it? If you were an engineer, you would, but if you're a mathematician, probably not. A theoretical guy like me doesn't actually want to solve the system. I just want to know if there is a solution. And then I just go back to bed. Anyway, that's mathematicians get a lot of jokes about that. We're very theoretical minded, so just have to deal with that. Okay, well, so far, any questions so far, guys? If you look at the title of chapter 2, it says matrices and linear systems of equations. I've talked a little bit about linear systems of equations so far, but I've said nothing about the other part of chapter 2, which is going to be matrices. It turns out that matrices are going to be the main tool that we use to study these linear systems. Indeed, to be able to approach this goal of solving linear systems. We're going to be using matrices to do it, okay? So that is the reality of it. Let me therefore take a minute to, I'll write that down as a note here. We will use matrices as a tool to solve or to study, let's say to study linear systems, because we might not be always solving them. We might just want to find out some things about them. So I'll say we will use matrices as a tool to study linear systems. That's kind of a good thing to keep in mind. I have one of my colleagues in the math department who says that everything you're doing in math, you're either the, what did he say? You're either the frog or you're the hawk. The frog is very concerned with the details, like exactly how you dot your I's and cross your T's at whatever the math problems are you're solving. But you also want to be the hawk. You want to have the broad view of what's going on. And I have to feel as your professor, my goal is to sort of be both the frog and the hawk from time to time. The big picture of chapter 2, the hawk perspective, is that we want to solve linear systems if possible, and we're going to use matrices to do it. That's really, in a nutshell, what these next couple of classes is going to be all about, right? So anyway, that's the hawk's perspective on it. I've got to take the frog's perspective now, which is also important, and get into the details of it. And this is a little bit, some of you have already seen matrices before, and so this is going to feel a little bit slow, perhaps. It's kind of a review, but we need to do it. First of all, maybe not everybody has seen this, but also just to get our notation kind of aligned onto the same page. So I'm going to start here with the definition now of a matrix. Okay, so we're going to give a definition for what a matrix is. So here we go. An M by N matrix. We're going to talk about this. So I underline the word that I'm defining. I'm going to put a little arrow with the word by next to that little X in the middle. Because when you see MXN, it's supposed to be M by N. And usually I will use capital letters for matrices. Try not to use lowercase letters. Use capital letters. I usually like to use the front of the alphabet. So capital A, capital B, things like that. And what is an M by N matrix? It is, this is an array. This is an array of numbers most of the time. However, it doesn't just have to be numbers. It could actually be not just plain old numbers. I'm going to say numbers or functions, right? It could be numbers or functions, interestingly enough, arranged in M rows and N columns. It is an array of entries, right? Which could be filled with numbers or with functions. And those are laid out into M rows and N columns. So rows, and guys, the rows go horizontally, right? They go kind of across left to right. The columns go up and down. Those are vertical as well. So that's kind of how this is going to look. Let me just write down an example of a matrix here that's pretty easy just to kind of get us started. with something to look at. I usually like to put this array inside of these big brackets here. So this is a nice way to spell it out. And then maybe I have the following entries. So maybe A has, the first row has entries of -3, 2, 1, and -1. And then on the second row, maybe I have a 2 and a 0 and a -2 and a 0. And then maybe on the third row, I have a 0 and a -1 and a 5 and a 2. This would be an example of a matrix. Can you guys, if you're anywhere near your chat boxes again, could I get you to inside your chat boxes? Let's hear from 36 people here. Type in what the dimensions, the size of this matrix would be. I just want to make sure people understand the M and the N thing that we're talking about here. As long as we get everybody to kind of agree on this one, I'm going to be pretty happy. Okay, yeah, this is awesome. I see pretty much uniform, consistent. In my first class was trying to get the 3 and the 4 mixed up quite a bit. So you guys have got it straight right off the bat, which is super. This is 3 rows and 4 columns, and I will sometimes just kind of add that kind of next to the matrix somewhere, just so we can see it easily. Yeah, this is a 3 by 4 matrix. Okay. Does anybody happen to know where I got the numbers for that matrix from? You can use your microphone or the chat box, whatever you want. Yeah, so a couple of you have already noticed that this is just coming from the example over here. These numbers, these coefficients in this linear system over here are literally just being used right now in the matrix. Guys, I don't know if you know the running joke of Math 250B, but the running joke is that the answer to every question in this class is to put it in a matrix. Okay, so if I give you a system of equations and I ask you to solve it, the answer to how to do that is put it in a matrix. You're going to hear me say that a million times. You're going to be sick of it by April, right? But yeah, that's basically what we're going to do. So we put the numbers in the matrix to start solving these problems. So just as a note, this is called, there's a name for this. This matrix, this is called the matrix of coefficients for the linear system. That is the matrix of coefficients for the linear system. So it's just grabbing the numbers out of that linear system and then just putting them into this 3 by 4 array in this case. Okay. Give myself a little bit more room to write here. Well, one thing you might notice here, guys, you might have already noticed this, is that this matrix of coefficients has ignored the numbers that are way on the far right side of the equal sign. Sometimes we're going to need to keep track of those numbers too. So I have another sort of way of talking about that. I'm going to make another definition. Sorry about all the definitions here tonight, guys. I know it's kind of a lot to deal with, but we do need these terminologies. So I'm just going to give you another definition right now, which is the definition of what's called the augmented matrix. So the augmented matrix, and this one will be written, so here's the notation, guys. I'm going to use this little pound symbol. It's the same one they use in music. When you're writing musical notes, they put, there's sharps and flats. And these are the sharps like a half step up from like A sharp or B sharp or whatever. So that's just the augmented matrix. And what this does is that this includes what's called the right-hand side vector. I actually am going to call this a vector, the right-hand side vector of the equations. So I think I'll write it down here in this example, and then I think you'll understand what I'm talking about. Okay, so for example, going back to this same example we've already been working with, the A sharp for this system here that we did earlier is just the exact same matrix that we wrote down a moment ago, but we now have one more column. And we're just putting the 5 in the far right column. And then on the second row, we would have 2, 0, 2, 0, and 3. And then on the third row, we have a 0, a -1, a 5, a 2, and a 0. This would be the A sharp. Notice that the size of this matrix, it now has one more column to it than the previous matrix A did. And so instead of 3 by 4, now we have a matrix that would be 3 by 5. Now, here's another thing, guys, that's really important, which is that the right-hand side values really should not be mixing up with what's on the left side. And so to help us not make any mistakes with that, I am absolutely going to want you to write a bar that is just to the left of that right-hand side. So now this becomes a vector, right? This is called the right-hand side vector would be this part here. Let me just emphasize that. This is the right-hand side RHS vector. Right-hand side vector, that just has the numbers that are in their far right column, or on the right-hand sides of the equal signs of my system in them. And then, of course, you have still the matrix here. This is the matrix A of coefficients that we were looking at earlier. So A sharp just keeps track of all of that, right? It has all of those values in it. Nothing is really missing. Okay, any questions so far?
So would that still be a 3 by 5 matrix or a 3 by 4?
The matrix A is 3 by 4, Fabiola, but then the matrix A sharp is 3 by 5. So it just depends which matrix you're talking about.
So even if it has that line to separate
Yeah,
the
the bar doesn't really come into play in terms of what the M and the N of the matrix is.
Okay, thank you.
Good question, good question. Any other questions so far? Okay, I tell you what, we are about halfway through our class. As you know, I always like to take a little break in the middle to give you a chance to kind of get away from thinking about this stuff, kind of clear your mind for 10 minutes or so. So I'm going to take a break. It's 6:55 right now. I'm going to take a break till about 5 after 7. Give you guys 10 minutes to decompress, take a break, talk to your friends, get some water, whatever. And then in about 10 minutes, we will pick this back up again. During the break, if you have any questions on the homework that's due tonight that you think might be good for me to go over here in real time in my Zoom, feel free to type them into the chat. And then when we come back in 10 minutes, I can take a look at that. So I'll see you guys in about 10 minutes. Well, guys, if you're out there within the sound of my voice, in about another minute or two, I'm going to start back up again. So this is a great time to kind of find your way back over to wherever you are cozying up to this Zoom session. And yeah, we'll start in another minute or two. All right, everybody. Well, it's about 5 after 7. I think I'm going to pick things back up again. I want to also thank you guys once again for those of you who are able to get a webcam turned on. That's really helpful for me to kind of see some faces out there and make sure I'm not just talking into the thin air here with no feedback. So I actually appreciate it very much. Luckily, we will be done with this Zoom class stuff very soon, so that will be a good thing. I saw your comment there in the chat, Bergen, about doing problem number 26. Should definitely have time for that, so just hold tight. I might kind of put it at the end of the session here, but we will take a look at that. My first class also asked me to talk about that one a little bit, so I will definitely do that. And if anybody else thinks of anything else they want to throw in the chat for homework questions in the next minutes ahead, feel free to do that. But before I kind of backtrack to the homework for tonight, I want to kind of keep my momentum going here. I just kind of, I got to start into chapter 2. By the way, we're covering like the first 3 sections of chapter 2, kind of all mixed together and all kind of at once. It goes by pretty quickly because it is fairly elementary standard material. So, I don't really have these sections split apart. I just kind of have all the material just kind of spilling out here in this kind of big lecture to kind of get this chapter started. So, we started the chapter by talking about linear systems of equations, and then I mentioned that we're going to use matrices as a tool to help us study those equations. Before we actually do that, before we go back to the systems of equations and start figuring out how to solve them, I actually want to spend some time just talking about the raw matrices themselves. Like if we have an array of numbers or functions, what kind of things can we do just with those matrices? Okay, so even if we take a step back from the linear systems and just focus on matrices, what kind of things can we do? So I've got a little section here for the notes on, I just want to talk about operations on matrices. And so I'm gonna have a few things to say here as well. So just to kind of set the stage on this, I'm going to let A be equal to an M by N matrix. So we just have any matrix. This would just be what? M rows and N columns in this matrix. And the first operation that I want to go over with all of you guys is something called transpose. I want to talk about this operation. So it's called the transpose of the matrix. And there's a notation for this, which is A with a sort of a capital T next to it. It's not really to be thought of as an exponent. It's just a transpose is the way you would say that. And this is the matrix. So this is the N by M, guys, be sure to keep your M's and N's straight here. So I'm swapping the M's and the N's here. So it's the N by M matrix obtained by swapping the rows and columns. Little typo here. The rows and columns of A. So if you just swap the rows and columns, you turn all the rows into columns, you turn all the columns into rows, that's called the transpose. So if I wanted to give an example of that, I would just say, well, from above, this is the reason I didn't want to erase my matrix A yet, because I actually want to do it for this matrix. From the above matrix A, you see we can transpose it into another matrix by just swapping the rows and the columns. So what do I mean by that? Well, I'm going to take the first row of A, and I'm going to now lay it out into the first column of A transpose. So the first column of A transpose would be -3, 2, 1, and -1. Okay? And then the second column of A transpose would just be the second row of A, which is 2, 0, -2, 0. And then the third row of A transpose is just, sorry, the third column of A transpose is just the third row of A. So you're just taking rows and columns and swapping them, okay? So any row or column of A then gets switched into the corresponding column or row of A transpose. And you can see when you write this down that it does have the effect of swapping the M and the N. So this matrix here is going to have 4 rows and 3 columns, and that makes it a 4 by 3 size, whereas the original A was 3 by 4. Okay? Does this make sense? You know, you might wonder why on earth would anybody do this? Like, what's the point? Why would you transpose rows and columns of a matrix? Well, I'm sure that if you've worked with a spreadsheet ever, you've had times when you wished that you could move the data around and turn rows into columns or vice versa. But it turns out that's only scratching the surface of what this is used for. Transposes are very important in things like doing projections onto what's called a subspace. It's also important for, let's say you have a bunch of data points and you would like to make a line that best approximates those data points. You can actually do that with linear algebra, but the formulas are going to involve transposing matrices. Actually very important for that. So there's certainly great applications, therefore, in applied math, statistics, anything where you have a bunch of data that you want to work with. So this is something certainly that although it may seem like it's just kind of a silly thing to do, it actually does have a lot of practical value. Okay, so transpose, that's one thing that we can do. All right. What other operations do I want to share with you right now? The second one, I'll put this as number 2, is, well, this is something we're all very familiar with, calculus. Right? We can do calculus with a matrix. So when I think about calculus, it's like, what kind of things do I think about? Calculus at its core is really all about limits. So I'd probably say that somehow I'm talking about combining limits with matrices. In that case, it might make more sense if it's not just a matrix of numbers. It would be more interesting if it was a matrix of functions. So maybe I should actually start off with that. Given a matrix function, let's say, I'm going to call this A of T. So now we imagine that the matrix has entries that are filled with functions. Then we can compute anything you can think of from calculus. Limits would be a great starting point. The limit as t approaches, I don't know, little b of a of t. we could do that. Now, how would we do that? So I want you to imagine that your matrix is not filled with numbers anymore, but it's filled with a bunch of functions. And all of those entries are just functions of t. Well, what I could be doing is taking the limit of every single one of those entries of that matrix as t approaches some value, right? So let's say that your matrix is 5 by 5. Then if I ask you to do the limit of the matrix function of a 5 by 5 matrix, I'm really asking you to calculate 25 limits, right? It's only one question, but it would be 25 limits because every single slot of your matrix would have a function that you need to take the limit of, right? Or we could do derivatives. So I could do a prime of t. And again, this would be 25 derivatives if it was a 5 by 5 matrix. You would be taking the derivative every single entry throughout that whole 5 by 5 array. And lastly, of course, another thing that I think of with calculus is integrals. So there you go. Ouch. That's a 25 integration problem. If it's a 5 by 5 matrix and I ask you to find the integral of it, I'm really asking you to find 25 integrals. Did your calculus professor ever ask you to do that? Probably not. And by the way, here I've drawn my integral as an indefinite integral. There's no limits of integration here. But certainly we could have those. It could be a definite integral, and we are doing definite integrals throughout this matrix. The important thing about this, though, guys, is that all of these operations right here, limits, derivatives, integrals, or whatever else you want to come up with, these are all done as slot by slot operations. So you're literally just going around every single entry of the array and doing whatever it is, the derivative, the integral, or the limit. It's just slot by slot. And so it's kind of common sense that that's what you would do. If you were stranded on a desert island and you had to get off the island, you had to figure out how to do the derivative of a 5 by 5 matrix. I'm pretty sure the first thing you would probably try to do would just be go through the 25 entries of the matrix and just take the derivative, right? That's exactly how you do it. So I won't do an example of that here because it is kind of very natural. But I should point out that this is not just a passing thought either. We are going to need to do calculus with our matrices in this class, especially, not surprisingly, when we go back to differential equations again, right? Differential equations are like a hop, skip, and a jump away from calculus. Many people would say they're actually part of calculus. So when I get back to differential equations, don't be surprised if you see matrix functions around that you have to take derivatives and integrals of, because it is going to happen. That is actually going to be exactly what we have to deal with. Okay, but for now, I just wanted to introduce this as a kind of a plausible idea that you could do calculus with a matrix. All right, but we really are going to spend more time, at least in the next few weeks, the earlier part of the semester, we're going to spend more time actually on number 3. And number 3 is actually even more basic than number 2 in some ways. We're just talking here about algebra. We're just going to talk here about algebra. If I want to do algebra, I might have to have more than one matrix in my hands. So let me just say here that we're going to take A and B. So let capital A and capital B be matrices of, I'm going to add a little phrase here and I'll explain it in a minute, of appropriate sizes. Of appropriate sizes. Is everyone able to read that? Not too small, I hope. Guys, I am keeping my eyes on the chat, and you can use your microphone too. If you need to communicate with me, if you can't see something, if it's not making sense, just slow me down. I get excited, and I can get on a real roller coaster of excitement, and before you know it, I'm like leaving everybody behind when I don't mean to do that. So just let me know if anything isn't clear here. So what kind of algebra am I talking about? Well, I've got several things in mind right now. One of them is, what if I want to add the matrices? A plus B. Now, right away, this presents a little bit of an issue. Because the way you would normally think about adding these matrices together would be you would just kind of line up the slots, right? The upper left corner, add it to the upper left corner, right? And you just get that as the result. And you would do that kind of all the way through the matrix. Well, that means that the two matrices have to be the same size, the M and the N. Can you imagine if you had like a 9x7 matrix and you wanted to add it to a 2x12 matrix? I wouldn't even know how to begin to do that. The shape of the matrices is not compatible. So that's what I mean when I say that these matrices should be of appropriate sizes. Okay, so we have addition. Obviously, we also can do subtraction. That certainly makes sense as well. Another thing we can do is something called scalar multiplication. So I'm gonna use a little k for a scalar here. So in your notes, you might want to mention that. I'm gonna be using scalars a lot with matrices. So k is a letter you'll see me use quite regularly for that. And what that means, guys, is, let me just write the words here. This is just scalar multiplication. So what you're really doing, a scalar is just a number, right? So how do I take a number times a matrix? Well, all you really do is, again, if you were stranded on a desert island, I'm pretty sure you'd figure it out. You just have to multiply each entry of the matrix by k. You just go through every single slot of every single row and column, and you just multiply those entries by k. So again, for all of this stuff so far here, this is still just slot by slot operations. So, again, what I mean by that is just you take the same slot from the matrices that you have, and you just do the operation within that slot. And you do it for every slot of the matrix. So it's kind of common sense. I'm not doing a lot of examples right now because this is just sort of natural, and I don't want to put half of you to sleep by going too slowly on stuff that's pretty easy. But now we come to something a little bit more interesting. Okay, guys? So I want to go to something a little more interesting now, which is, what about just matrix multiplication? So what if I have A and B and I want to multiply them together? So this would be written as matrix multiplication. So it turns out, guys, that this one is not done in maybe the natural way or the most obvious way that you might be thinking of. So I need to spend a little bit of time. I'm gonna put a little asterisk next to that on that matrix multiplication, and I'm gonna come down here and I'm gonna talk about it a little bit more detail. So matrix multiplication. So this turns out to be a little bit weird. What we're gonna do here is going to be a little bit weird, starting with the fact that the two matrices that you're multiplying don't have to be the same size, the way they did for addition and subtraction. Here, the matrices might not be the same size, but there is a requirement, and I'm gonna express it for you now. Basically, here's the setup of this. Given the matrix A, which is M by N, okay, and the matrix B, which is N by P. Ooh, so there you go. These two matrices don't have the same size, but they do have one thing in common. You see the N? The number of columns of A and the number of rows of B are matching up. That's actually required, right? So this number, let's just get clear about that. This number has to match right there. The number of columns of A has to agree with the number of rows of B. And if it does, we can form A times B right here. And this matrix will have a size that will be M by P. Okay, so we can form A times B as, well, so this is a new matrix. We form the matrix A times B. So I would like to show you how this works. It's a little weird. Okay, so everything up until this point is just kind of natural, transposes, addition, subtraction, derivatives and integrals. Nothing weird at all about any of that, but now we're hitting something that is a little bit weird. So let me give myself a little more room here and we'll talk about it. Because it's a little bit weird and people are maybe not comfortable with it right away, there must be like 5,000 YouTube videos about this. So if this ends up being a problem for you and you need a little extra practice with it, you can look online as long as you want and you're going to find some good examples of it. I'm going to show you how to do this matrix multiplication using an example. So I'm only going to do one example right now, guys. And I'm going to leave the rest of it to you to kind of learn how this works. But it's not too bad to do this. I think with one example, that should be pretty good, hopefully for most of you to pick this up. So let's do an example. Let's suppose that A is the matrix 1, 2, 3, and then followed by 4, 5, 6. So the first row is 1, 2, 3. The second row is 4, 5, 6. And then for the second matrix, B, I'm going to use a slightly bigger matrix, even though I didn't give myself a lot of room here. The first row is -1, 0, 2, and 1. And then the second row is going to be 2, 1, 1, 0. And the third row is -1, 3, 0, and 1. Let's take these two matrices, A and B. And what I would like to do here, guys, with you all is compute A times B. I just want to practice calculating A times B. All right. So in order to do this, let's first of all just make sure that this actually does work. Can you guys, in your chat boxes, this is partially to make sure you're still there, could you please type the size of the matrix A? So I would like to know what is the M and the N, and just put that in there for me so I can kind of see that everybody's following the notation here. Yeah, 2 by 3, right? Great, I love it. How about the size of B? Go ahead and throw the size of B in there for me. Okay, seeing lots more good answers. Yeah, 3 by 4, right? So A is 2 by 3. So is this going to work? If I take a 2 by 3 and here I have a 3 by 4, am I able to do that matrix multiplication? If I look over here, what does it say? As long as the N values are matching, right? So in this case, the N is the 3 right here, right? So that's the N value of 3. And since that matches, we can do this calculation. Awesome. Yes. So great. And then the size of A times B, what will be the size of A times B real quick? Everybody went dead on me out there. Yeah, it's a couple. Oh, there it comes. Sorry, my computer's just slow. Yeah, it's 2 by 4, right? We're gonna have 2 by 4. Exactly. So the M, it says it right here, right? M by P. M by P. So in this case, that would be 2 by 4. So let me set myself up with kind of space to put 2 rows and 4 columns. Guys, the way you do this calculation, let's say I want to calculate the 1, 1 position, the very upper left corner of this matrix. The way you're going to do that is you're going to take the first row of A and the first column of B. So it's always going to be rows of A and columns of B. And what you do with those two things is you dot them together in the sense of a dot product. Okay, so I don't know how well everybody remembers from there. Usually in Calc 3, we use the dot product for a lot of things. So if you took Math 250A or something equivalent to that somewhere, you would have used this dot product where you kind of you know, you take the corresponding entries of the vectors, you multiply them together and then add them all up, right? So that's exactly how you do this. And again, you can watch 5,000 YouTube videos of people practicing this, but that's the idea. So here, I would take this first row, which I circled, this first column of B that I circled, and I would dot those vectors together. So I would take 1 times -1 plus 2 times 2 plus 3 times -1, right? So that's -1 plus 4 plus -3. And that adds up actually to 0. Does that make sense? So I'm doing a dot product. I'm taking the vector 1, 2, 3. I'm viewing that row of the matrix as a vector. And I'm dotting it with the column, the first column of B, which is this vector -1, 2, and -1. Now, when I move over to the right and I want to do the next entry right here in the second column, first row, second column, the only thing I need to do is switch to the second column of B. I still use the first row of A, and I dot it now with the second column of B. So I'm going to get 0 plus 2 plus 9. Dot products, guys. 1 times 0 plus 2 times 1 plus 3 times 3. That actually adds up to 11, right? 0 plus 2 plus 9. That's 11. Okay? To get to the next entry, I just move over to the third column of B and I do the same thing again. I take the dot product of the first row of A with the third column of B. That's 1 times 2 plus 2 times 1 plus 3 times 0. 1 times 2 plus 2 times 1 plus 3 times 0. That sounds like that adds up to 4. And then the last one, guys, is to take the far right column of B. And again, I'm dotting the first row of A with the rightmost column of B. And that's 1 times 1 plus 0 plus 3 times 1. And that also adds up to 4. What do you guys think? You understand that so far? Reasonable? All right, here's what I'm gonna do. I'm gonna shut up for 60 seconds and let you try to do the second row. So to do this second row, you're gonna take the 4, 5, 6 row of A, right? You're gonna take that bottom row of A, and I need you to dot it one at a time with each of the 4 columns of B, and I'm gonna have you come up with 4 numbers, okay? And in a minute, I'll ask you to put those in the chat. But for right now, don't put them in the chat quite yet. Just go ahead and calculate them for me. I'll give you 1 minute. I'm guessing most people have had close to enough time. Whenever you feel ready, feel free. Anybody who's brave out there and wants to test out an answer, I'll take as many people. You can type your 4 numbers into the chat, and let's just see how people are doing. If anybody is agreeing with anybody, that'd be a good thing. That's usually a sign that people are on top of what's going on here. So I've had a few answers. It's absolutely 100% consistent to me, it looks like. Yeah, it should be exactly what you guys are coming up with, it looks like. So we have a 0, and then a 23, and then a 13, and then a 10. Okay? And again, this just takes a little practice. You're just doing dot products of rows of A with columns of B, right? And if you're not sure what's going on, guys, I get it. Like sometimes I feel like I'm the only one in the room who didn't understand something. If you're feeling like that with this thing, totally understandable. I have not exactly spent a lot of time on this. What I'm going to recommend is that, just everybody needs to get on top of this. I don't want to spend a lot of time on it. go online and check out some YouTube videos or come to my office hours and I will spend more time, give you a little more practice with this. We actually need to be able to do this. I've been a little surprised in recent semesters. I get towards the end of the semester where we have to start doing matrix multiplications again, and I'm a little surprised sometimes that it seems like not everybody kind of had it down. So if that is how you're feeling, no worries. It's totally normal, and you might need to practice it a little bit more. The homework you're going to do for next week will force you to practice this a little bit more. So you will get more practice on it, and I'm here to help. So I don't mean to, I'm not blowing over this to suggest that it's not important or that, it should be just totally trivial. Certainly you might need to spend a little bit more time on it, and that's totally fine. Maybe Audrey will even have one or two of these to keep you on your A game, to practice, for those of you who are able to go to her session. So,
This Thursday, we'll be multiplying matrices. I
yay! Okay,
promise you.
well, get a little practice in the session as well if
Yes,
you
do
guys are
do
able
come.
to. Okay, very good. So, guys, I feel pretty good about this calculation overall, but you know what? There's at least two things about what's on my board right now that has me feeling really queasy, and I want to spend these last. I'm going to spend maybe 5 or 10 minutes on this issue, and then we'll save the last 5 minutes to talk about that homework problem. But there's a couple things here that has me a little bit worried. The first one is that when I'm talking about numbers, I can do addition, subtraction, multiplication, and division. And what I'm noticing here is that I didn't put division in my algebra list. I never talked about taking A divided by B. And it turns out that we can't not do that. We cannot divide one matrix by another. I had even suggested to my publisher of the book, I had said, should we put a little remark in there about that? And my publisher said, no, don't even mention it. Like, don't even give people the wrong idea. You cannot divide one matrix by another. Okay, so that's one problem. Now we're going to have kind of a workaround on that. And on Thursday, I'm going to be telling you about that. Okay, so there is a workaround for not being able to divide by matrices. That's one issue. But I have a second thing that's making me queasy right now that I actually want to talk about right now. And I'm going to put this into the notes as a follow-up. And my follow-up is going to be, let's just try to do this question. What is B times A? This would be another chance to practice matrix multiplication. So take a look, and I'm using the same matrices that I have at the top of my board here, and I'm wondering what would you say to me if I wanted to calculate B times A? Fadi's got something. I don't think it's solvable. What's the problem here?
So, can you see me? Can you hear me? Sorry.
Yeah. What's going on?
So, for the first one, when we multiplied A by B, the inner size was n matches, so 3 equals 3. But if we try to
Right.
do the other way around, it won't match. It put 3 by 2 and then 4 by 3, so it doesn't match.
That's exactly right. B is 3 by 4, and A is 2 by 3, and now I'm violating the rules over here for the dimensions of the matrix. These two numbers are not matching, and so this actually is impossible. This is impossible. We cannot calculate B times A in this case. And in fact, this is just a observation of a more general problem that we have, which is that in general, everybody needs to make this observation because this is a big deal. In general, matrix multiplication, which is what we're talking about right now, matrix multiplication is not commutative. In other words, if I take A times B, it's not at all guaranteed, let alone even expected, that it would agree with B times A. And in fact, even if both products do make sense. Even if let's say that A is 3 by 3 and B is also 3 by 3. If the two matrices are both 3 by 3, then I can multiply them in either order and I have no problem with the sizes here. But this is even if both products exist. It is usually not going to be true. Now, I won't say it's never true. If the matrix A has all zeros in it. If you have a matrix of all zeros and you multiply it by anything else, well, okay, doesn't matter what order you do that in, you'll get all zeros. Okay, so you could get lucky, right? You could get, if you take two matrices, you could get lucky, and maybe once in a while, I mean very rarely, but once in a while, maybe you get lucky. A times B equals B times A. But usually it's not true. And that lack of commutativity is, well, I want to say it's a bad thing, but actually in a way it's a good thing because it's what I did my PhD on. So I probably wouldn't even have a job right now because I studied non-commutative algebra in grad school, and I did a lot of research on it. And this is really the first place where students will see kind of this non-commutative behavior. And it takes a little getting used to because all our lives we do math, we think, oh, we can multiply the things in whatever order we want. It doesn't matter. Oh, but now it does. Let me show you a couple of examples of what kind of things can go wrong. This is where we're gonna wrap this up for today. I'm just gonna show you a couple quick examples, and then we'll do that homework problem, and then we're gonna be good to go for Tuesday. Yeah, so over here, I'm going to show you some red flags, right? I'm going to show you some examples of things that can potentially go wrong. So, for example, if I had B A C A B B C A B, right? And I had all those matrices just multiplied together. Like your natural inclination is, oh, let me simplify it. Let me put all the A's together, all the B's together, all the C's together. You can't do that. You have to live with it like that. And you cannot clean it up, right? So this cannot be simplified. That's kind of, that's kind of bad news. We can't really do anything with it. Just have to live with it the way it is, okay? Even something that might feel a little bit more standard. If I wanted, so let's say I wanted to take something pretty familiar looking from algebra, just say A plus B squared. By the way, when I put a power on this matrix, it means exactly what you think it does. It just means take that matrix times itself, however many powers you have. So in this case, it is correct that this is A plus B times A plus B. And it is also correct that you can FOIL that out. And I'll talk more on Thursday about some of the other properties of matrix multiplication. But it is okay to sort of just FOIL this out. So A times A plus A times B plus B times A plus B squared. That's okay. But the simplification ends there. I cannot take the two terms in the middle, which is the AB and the BA, and like combine them together. In high school algebra, you would have done that. You would have written that cross term as 2AB. Right, so here, this also cannot be simplified any further. We can't do any more with it than what we've already done there. Okay, and then let me give you one more. And then we'll move on to that homework problem. One more example, and this is one that a lot of people are guilty of doing. I probably did it when I was kind of a novice at this stuff myself, which is, let's suppose that you, what I'm about to write down is, this is illegal. You can't do this. If you have B equals C, let's just say you have a couple of matrices that are equal to each other, and you say, oh, I want to multiply the equation through by A. I see people do this all the time. I just want to multiply through by the matrix A. So if I wanted to do that, would this be okay? AB equals CA. Oh, you know what? The order matters here. I'm gonna put a big slash through that. It is not allowed. You know, the trouble with this is that what I did here is I put the A on the left side of the B, but then I got lazy and just put it on the right side of the C. And because order matters, well, then I haven't done the same thing to both sides of the equation. Whatever ever E does to one side of the equation, E must also do it to the other side. Well, we didn't do that here. We multiplied the left side by A, but on the right side, we put the A on the right side. Okay, that's also not legal. So we have to be really careful here. Okay, you can multiply the equation through by A. You just have to be careful that you're doing it the same way on both sides of the equal sign. Okay. 10 minutes ago, we wouldn't have even given that a thought, right? Until we realized that matrix multiplication order matters, right? Until we realized that, we might have been sloppy with something like that. And so I'm hoping that now you guys are going to be like pretty familiar with that and not have any more issues with it. Okay, so I've talked a lot about this property that doesn't work. So on Thursday, I promise I will come back with a bunch of good news for you about properties that do work with matrix algebra, and we'll make a list and we'll kind of make sure that everybody feels comfortable with them. But this is the one that doesn't work, and it deserves a little extra attention just because it is kind of maybe surprising in some ways that we don't have that. Are there any questions here on this discussion of matrix multiplication and kind of order mattering on these products? Is everybody feeling okay with it?
Quick question, actually.
Oh yeah, please.
That last example is just to show that when B equals C, that AB does not equal CA, but that AB can equal AC.
Correct. I maybe should put that here, a correction that we could offer. And that's a really good point, Bergen. I'm glad you brought that up. Is that we can start with B equals C, and I can multiply it by A as long as I do it on the left of both sides. Absolutely. And I'm glad you brought that up. That's a really good point. Okay. Any other questions, guys, before we take 3 minutes to look at that homework problem that I think somebody wanted to ask me about? Okay, so guys, just before we wrap this up for tonight, the homework problem that I think people were asking about is this Sherlock Holmes murder mystery problem. So changing gears back to the homework that's due for tonight. This is, of course, a Newton's law of cooling example. And one thing that a few students in my first class were kind of doing with it is they were actually going all the way back to the differential equation for Newton's law of cooling and solving it from scratch from there. And that actually you don't need to do, because in my videos and in your notes already, right, we solved the thing. What's really important to use is this result of solving Newton's law of cooling. And I'm just going to put it on my board here. You would have this already in your notes as the general solution to Newton's law of cooling. So actually, this problem is not really a differential equations problem at this point. What it is more is just, okay, it's a word problem with a bunch of numbers, and we got to put the numbers in the right places and solve for something, right? So for example, I think they told us in the question that the temperature outside was, I think it was 34 degrees. This is by the way, I don't have the whole question in front of me. This is a big word problem. So for those of you who haven't looked at this yet, you may just want to take a few sketch notes now and then read the question more carefully to get the details. But all of the given information in the problem is going to allow you to solve for the T sub m, which that one I think is just directly given. There's also a C2 and a K. that you have to figure out what those are. And they did tell you that at 2 p.m., I'll kind of sketch the other information here. The temperature of the victim of this murder, the temperature was at 38 degrees, I believe. And then at 3 p.m., the temperature went down to 36 degrees. The main point, guys, on this problem is that this information here is enough for you to figure out what C2 and K are. But in order to do that, there is one very important thing that you have to decide sort of before you really dive into this. And that is, at what time are you going to start your clock? Your little t, right? Your little t is the time variable. And when is t equal to 0 anyway? Is it at midnight? Is it at noon? Is it at 2 p.m.? Is it at 3 p.m.? Like, when is t equal to 0? This is something you kind of have to figure out near the beginning of solving this thing. It turns out it doesn't matter what time you choose. From a conceptual point of view, it doesn't matter. However, if you want the numbers to be nice, I'm going to give you a little hint. And the little hint is that you will want to let little t equal 0 at 2 p.m. And then little t would be 1 at 3 p.m. So I want you to measure time in hours. Don't measure it in minutes or years or anything like that. Use hours because that's kind of consistent with the data that's given here. And so they basically told you that at time 0, the temperature is 38, and at time 1, the temperature is 36. You can plug all that stuff back up into here and solve for those constants. You're gonna maybe need to use a calculator. There'll be maybe some logarithms that you have to take, right? If you're trying to extract these exponent values. So don't be afraid of a little bit of algebra, a little bit of calculator work, but you can solve for all of those parameters. Once you've done that, you are simply going to take that temperature function with all of these numbers plugged into it, and I actually off the top of my head don't remember what they all are, but you're going to set that equal to the normal body temperature of 98 degrees, and now you're going to solve for little t, the little time t. And by the way, it will turn out, if you do it correctly, that value should be -4. And that means 4 hours before 2 p.m. is when the body temperature was 98 degrees. The time of the murder was 10 a.m. So it turns out the answer to this question is yes, Sherlock was correct. And you just need to do the crunching of the numbers here to show that that is right. One last thing, and then I'll let you go because I know that I'm kind of out of time. But if you go to our Canvas page, just to show you really quickly, there is a, under Pages, this is where I keep all the videos for this class. There is a link here that says additional videos on it. And so if you're struggling with Newton's law of cooling, you can go into that additional videos section and, oh, well, right there at the top of the screen, you can see that. There it is. Oh, a 7-minute example of Dr. Annan solving a Newton's law of cooling word problem. So there's, resources like that that you can find in Canvas. If you get stuck on a problem from the homework, you might check out the video section. There might be something there that's similar that you might be able to use as a guide. So does that at least get you started on this one? Decent for now? Okay. Guys, that is all I've got for tonight. Wow, 2 hours goes by fast. I am going to take like a 5 to 10 minute break to kind of get myself situated for my office hours. But I will be going over to Zoom, my office hours Zoom room for most of the rest of the evening. If you do have some questions, feel free to pop in over there. But I just want to thank you all for being here tonight. I'm really grateful to you for putting up with my remote situation this week. We'll be back in this same Zoom room one more time on Thursday. And then next week, unless something really crazy happens, we should be back in person for the rest of the semester, having a normal in-person class. So with that, I'm going to wish you all a great evening and thank you for being here. And I'll see some of you in office hours perhaps, otherwise Thursday for sure. Have a great night, everyone.
Thank you.
Thanks, Dr.
Bye-bye. You're welcome. Bye-bye.